Okay, so last class, we learned how to use the water analysis, the water analysis and the gas analysis, and we did not cover the oil analysis. Today we will do an example. We will create an example where I will go through the details of how to add an oil analysis in the software. But last time we had a gas well, we created the brine, we learned how to enter the data, did a balance charge, talk about the different options for charge balance. Then we reconcile that brine in order to obtain a representative brine sample. Then we also learn how to enter a gas, create a gas. We enter the data in mole fraction, then reconcile the gas and obtain our gas for the calculations. After that, we mixed, we took the brine and the gas to reservoir saturation. We used the saturator tool. We entered the streams for study, the brine and gas, and the respective flows. We also entered some mineral data to saturate with minerals. And then we reviewed the chemical changes and we created a representative reservoir fluid. And then we studied this scaling risk using the tool for the scaling scenario tool, where we brought the reservoir fluid, put it in the scaling scenario, and we entered different process conditions, temperature and pressures, and we also turned on solids and reviewed the results. So today we are going to do something very similar, but we are going to learn a little bit more about the tool, the analysis, and we are going to learn how to enter an oil analysis. Okay, so in this case, we are going to create a bathos well, and in this well we are producing a brine, a gas, and an oil. And in this chapter, or in this example, we are going to learn this, how to enter the oil analysis, and we are going to learn how to recreate a representative fluid also at reservoir conditions, just as we did it in the last class. So we are going to follow the same steps, and we are going to reinforce what we learned last time, okay? So I think my colleague Dira also sent the file that we created yesterday. If you needed it, I think that was sent to you. I also sent to some of the attendees. I also sent the file that I created yesterday in class. If you needed it, you should have it available to you. If you followed along, we are going to work in that same file. So please go ahead and open your file. Okay. And let's save that new file as ScaleChem Training Day 2. And then click on Save. Now my name changed. Okay. So now,
Diana, what if you didn't receive that file? Was it sent to everyone?
Yes, it was sent to everyone yesterday in a general email.
I don't think I got that.
Are you sure about that? I didn't receive the file either.
Let me double check. I'm positive. Okay, let me see. Yes, yesterday, Dira Silvera sent a let me see. If not, I can just, if you just give me your emails, I'll just quickly send this to you. Yes, it's called SCB class session 1 recording plus case file. She sent it to all the training participants with a link to
It says
download it.
ScaleChem training day 1.
Yeah.
That's the file.
Yeah,
Sorry.
that's the file. That should be the file.
It said unexpected file format and then closed.
Which version of the software do you have?
The software is version 10.
Oh yes, that's the reason. The file I sent is all created in version 11. So if you worked in your file yesterday, you can use that file. Or I could try to send you the version 10. Do you have the file that you worked on yesterday?
The file from Monday I've got open at the moment. It was ScaleChem basic training day 1.
Yeah, the same. Yeah, that's that one.
I've got that open now. So that's got the Olympus, brine, production gas, reservoir and contour, mixing water and seawater files in the navigator window.
Mm-hmm. That is the file. Perfect.
Okay.
Um,
I'm sorry, I have the same problem, and I have the version 10, but I can open the ScaleChem training day 1, but I can't see any of the Olympus data. I only see add brine, add oil to the left. But I can see the plot from yesterday and the data in the design and everything, but I cannot see the, yeah.
so everything disappeared, it seems. Just try to add an icon. Just click on any icon, and maybe that will bring everything.
No, because the action, there's no navigator, it's only the action folder. So maybe there's some.
So maybe
Yeah.
you don't have the navigator, right? So that means that you can go to View, Toolbars, and click on the navigator so that it shows.
Yay! Thank you.
Okay.
Yeah.
Anyone else having a problem with just you can simply open the previous example, the example that we did on Monday. Okay. Yes, if you have your own file, you can go ahead and use that. If not, stop me and I'll send you the file. Okay. Okay, so now we are going to continue working in this file. The reason why is because we will be using this Olympus reservoir and the Bathos reservoir that we are going to create today to learn how to use the facilities. Okay, so that's the reason why I want to continue working in the example that we created on Monday. Okay, so with that being said, now we are going to create the bath as well. So first step, the first thing we are going to do today is create a brine analysis. Okay, so we go to the Actions pane and double click on that brine analysis. That brings the icon to the navigator, and we are going to double click on it and change the name of the brine to Bathos brine. Okay. So if I bring the presentation in here, in this table, you can see the information that has been given to me. So I have the cations, the anions, the neutrals, and some of the measured properties. Okay, so in this case, for the bicarbonate, and I see in the chat there was a question that says, is there a way with the ScaleChem if you have a pH value and an alkalinity value, so you can perform a carbonate speciation? Determine the bicarbonate value using equivalent way from alkalinity value. So I hope that with this example I covered this question. So I'll show you how the software can, with the pH and the alkalinity calculation, you can calculate the alkalinity value. Okay, so in this specific example, they are not giving me a bicarbonate concentration. they are giving me an alkalinity value, okay? And in this is a case where we have measured a total alkalinity, but not the inorganic carbon. So in this case, you'll see that down here we know that the acetate ion, this is the acetate ion down here. Let me just put my pointer. The acetate ion is also contributing to the total alkalinity as well. So what this means is that if you don't have a value for the inorganic carbon as bicarbonate, the initial guess for the bicarbonate will be this total alkalinity value. And when you see this type of information, like if you're given this type of data, this means that you can use the pH and the alkalinity reconciliation option in the software in order to back calculate this alkalinity value or this bicarbonate value, okay? So let's go back. Let me just bring the software. And what we're going to do now is to start entering the data I just showed you, okay? So for sodium, we are going to say that this was 15,260. For potassium, 180. Calcium is 850. Magnesium is 135. Strontium is 65. Barium is 1.3. And also in this specific well, in this specific water or brine, we also have some content of iron. So that's 2.1. For the chloride ions, so we have 24,500. For sulfate, we also have sulfate ion, so it's 160. And again, now in here, for this bicarbonate, we don't know. We don't know what is the value of bicarbonate in milligrams per liter. But the report says that the total alkalinity value is 673. So we are going to enter that value just as an initial guess. We know that the total alkalinity value is including this bicarbonate and is including this acetate concentration. But we are going to put the alkalinity, the total alkalinity, as an initial value for this bicarbonate. So let's enter 673. And for acetate, it was a value of 386. Okay. For neutrals, we were given that we have some boric acid, 107, and also some silicon dioxide, that is 60 milligrams per liter. So this is the information in the brine analysis. To the right, you can see the ion charge balance. So the cation charge was calculated, the anion charge is calculated, and there is a positive imbalance. So when we have a positive imbalance, and if we have selected the dominant ion balance option, the software calculates that we need, or it needs to add 409 milligrams per liter of chloride to reach electron neutrality. Okay, so that is what the software has done here. Now the next step is to enter the measured properties in our reconcile window. So to do that, we click on the reconcile button, and it brings us to this screen here. And in here, again, these properties were probably measured at 25 degrees C and 1 atmosphere. The pH of this sample was measured to be 6.7, and the density value was also given is 1.026. Nothing else was given, just those two measured properties. The software will calculate the other properties even if we don't have them. Okay. So I want to go ahead and just leave it as concentration data only and see what the software calculates. Just I'm curious. You have any question? Somebody has any questions? Okay. So what we're going to do here is let's go ahead and calculate just to see what the software calculates. Okay. My machine is a little slow today. Oh, and also the alkalinity value was given to us, so I did not put that one in there, but I will have time to put it. So this is what the software is calculating only using the concentration data. Okay, so 7.59 or 7.6 versus the measured value 6.7. The alkalinity value was actually 673. I didn't put it, but I will put it now. 673 versus this 850 calculated based only on what we enter, right? And then we also have the density and the electrical conductivity. So we are really far away, especially for pH. It's almost 1 unit of pH. And also we made an assumption for the bicarbonate ion. And so because of these two reasons, the pH and the alkalinity are far away from only using the concentration data only. What we are going to do next is to select the option measured pH and alkalinity. Okay, so make sure you enter here for the alkalinity value, the measured value of 673. I just forgot to enter it. And select the measured pH and alkalinity option and go ahead and calculate. Now, what the question that we should ask ourselves here is like, what will the software do now? So, how much of the chlorhydric, how much of the acid or sodium hydroxide will add to match the pH? How much of the bicarbonate or that will be inorganic carbon, carbon dioxide, the software will add in order to match alkalinity. So whenever the software is doing adjustments in your composition, specifically for pH and alkalinity, the software will add this table down here. So you'll see that in order to match your pH to 6.7, the software is adding HCl. And as you remember, we calculated that this was a 7.6 value. So it was a little bit more basic. So in order to decrease that pH, the software added chlorhydric acid, a total of 106 milligrams per liter of that of HCl. Okay. Now, for the carbonate, to match this bicarbonate value to 673, what the software is saying is that it added, in this case removed, because we have a negative value here, it removed a total amount of CO2 from solution, right, of 43.4 milligrams per liter. Okay, so that when it removes that amount, then it will match this alkalinity value here. Okay, and this one we already knew. This is the charge balance, 408 milligrams per liter to reach electron neutrality. Okay, so just to let me just go back here. So what did the software do here? We already knew the alkalinity value, right? That was 673 milligrams per liter. The software also knows the acetate ion. So what the software now did is that based on the alkalinity value and based on the acetate ion concentration, it could now back calculate the amount of bicarbonate in the solution. So that's what we accomplished by selecting the measured pH and alkalinity value. okay? Because we had this total alkalinity and this concentration of acetate in solution. And these are the calculations that the software does in the background. So it basically, what it does is it's removing CO2, right? It's removing CO2. So to match the bicarbonate, we need to know how much of that, we need to know the molar ratios. So in here we have the ratios of bicarbonate and the ratio of CO2, that's 1.39. And then we multiply that by the value that was removed, and that gives us the total bicarbonate that was actually removed from solution or changed from solution. Okay, so any questions about this?
Quick question.
Sure.
Yeah, so on the data entry tab, we did not add any CO2.
No, no.
But then on the reconciled, we took away CO2. So how did that work? Did we generate CO2 in this?
No, the software uses CO2 to balance inorganic carbon. So what the software is saying, okay, so if you want to remove or add bicarbonate, the software will remove or add CO2 instead. And this is what it does in the background. So if you are removing CO2, in order to translate it to bicarbonate, you need to make this calculation. Okay, so you have your molar ratios here of bicarbonate versus CO2. So in order to find out, this is a manual calculation that we will need to do to have an idea, instead of CO2, how much of the bicarbonate was removed. So we have the molar ratios of CO2, bicarbonate and CO2. Then we get the molar ratio 1.33, and then multiply, in this case, for this specific example in the slide, not in our software, but in the slide, it's saying that the software has removed 66.9477 milligrams per liter of CO2, but you want to translate that into bicarbonate ions. So you put that ratio multiplied by the 66.95, and this is the actual amount of bicarbonate that you remove from solution.
That makes sense. Okay, thank you.
Yeah. So ideally, I would love that we could do it with bicarbonate because you can actually see it. But no, the software uses this molecule, the CO2, because it's just easier to just keep electron neutralities and all of this balanced in solution. So we cannot do it with bicarbonate, so the software uses CO2. It's just a mathematical trick in here. But that's what the software is doing in the background. Okay, so it's just to match that inorganic carbon. That was a good question, so I could explain in more detail. Okay, so now that we have calculated the properties of the solution using the measure pH and alkalinity option, the software is saying, okay, your brine is supersaturated with barite and calcite. And I want that you click on the report tab, okay? And in here is what I want to show, where you can find what was the percentage of changes that the software did in order to reach electron neutrality. That was a question, that was something, it's related to the question that we had on Monday. So click on customize. That table is not shown. We are going to bring this, we open here in customize, and you'll see that there are a bunch of tables here, right? The only one that is being enabled is the brine summary. All of this that we see here is the only tables that we are seeing, but you can see way more than that. You can see charge balance, you can see reconciliation summary, you can see the species output, all of these options, partial pressures. For what I want to show, just click on this charge balance box and then click OK. Okay, so that means that we need to scroll down and look for the charge balance table. And in here, the software is saying that since we had a positive imbalance, it added a specific amount, an extra amount of chlorides, was 400 and something, 408.5 milligrams per liter. And this is the difference, the percentage in difference. So if you have a value, let's say you don't want to exceed more than 5%, you can come here and double check that number. If you have a 20% here, if you see a 20, 15%, then it should indicate that you should go back or to the lab or double check your numbers that you have entered here in your data entry. Okay.
That's good to know.
Yes, it's very nice. But just as a point, I was also talking to my colleague, and he said that this was actually we had a previous before it was in a studio. And this probably was like 10 years ago. This value was actually shown in the interface. So I will ask as a feature request that we can actually put this in my interface, right? Here, somewhere in here that tells you that difference. So you can make sure that you're not making any mistakes. That's a good feature. And thank you for highlighting that. I will talk about that with the developers. Okay. So that is one. Again, you can always bring more information. This is what we showed you here, but you can always, if you are more, if you want, I don't know, not fugacities, but how much for the reconciliation for alkalinity, what did the software do, right? In here you can see how much of the CO2 was added and all of those things for the reconciliation summary as well. And in here you can also see that the software is saying that the alkalinity pH titrant was H2 sulfuric acid. So you can get more information, more detailed information here. Okay, so that is the brine analysis. Now we are going to move to the next analysis that is going to be so simple. Oh, this is the reconciliation options, and here is just a slide that I want that you have where we can show. I am showing the details of what every single reconciliation option means. So we have worked in this class, we have worked with the concentration data only, and today we did the measured pH alkalinity only. But you have 3 more options that you can explore: the gas phase content and what it does. Here is what the software does and what it moves and what it adjusts, the measured pH only. And also we have, this is a new option that we added in version, I think it was in version 10. So let's say you know your total inorganic carbon. You also know your total alkalinity and your measured pH. So you can reconcile using these 3 information points as well. So you can explore using these tools or these different 3 different ways of reconciling a solution, a brine. Okay, so the next analysis is going to be the oil analysis. Okay, and this one is a little bit is time consuming because the oil analysis itself, you want to enter the data, right? But when you go to the software, we have so many different options that I just want you to understand what are the options and how you can enter that data. Okay, so we're going back to the actions pane and select, double click the add oil analysis. Okay, this will bring a new icon to your navigator. And let's rename this as Bathos oil. Okay. So for this analysis, we were given a distillation assay, and we will learn how to enter this distillation assay. Notice that when we bring this oil analysis, there are 1, 2, 3, 4 different tabs. So we have the combine tab, the pseudo components tab, the assay tab, and we are also familiar with this one, the reconcile tab. That is the one that we use to calculate the properties, in this case, of the oil. So let me start with the assay. So in this assay tab, and here is where you enter a distillation curve. So as I mentioned, we are going to learn how to use this tab because for this example, it was given an assay. That was the oil analysis that was given to us. Okay. For the pseudo components option, let's say that maybe you already have converted your distillation assay into different pseudo components, okay, by using a specific another thermodynamic method or model. So you have breaking your distillation. You have your distillation assay, and you already have your pseudo components. Okay, so what the software allows you to do here is to enter those specific pseudo components with the molecular weight, normal boiling point, specific gravity, and the most important one, the mole percent for those specific pseudo components. Again, you will need to use another thermodynamic tool to create those pseudo components, and then you come and enter them in here. There is the combined option, and in this specific tab is where you enter pure components. Okay, in this list, for example, you are seeing only alkanes, which could be methane here, methane, ethane, propane. Okay. But you can also enter alkenes or alkynes. You can also enter aromatics, and you simply enter them down here, right? You just, if you know the, I don't know, benzene, so you just simply enter the name down here, and it's recognized by the software, and you can enter that composition. Just if you happen to have benzene in your composition. So in here is just pure data. You can also enter gases such as nitrogen and CO2 and sulfuric acid. Okay, so for our example, the oil that we want to create has 2 inorganic components in the composition. It has nitrogen and it has CO2. So we are going to enter the composition of those inorganic gases here, or inorganic components here. So for nitrogen, this oil, it was found that we had 0.5 mole percent. So let's enter that value in front of nitrogen. 0.5% in the composition of the oil. And for CO2, the oil also had a 1.1 CO2 composition. Those are the 2 components that we have, at least in this, that we are going to enter in this section. Okay, so this gives us a total composition of 1.6 mole percent of these inorganic components in the oil phase. And now we need to enter the remaining 98.4% of this oil analysis. Okay. Let me just, you can see that there are a bunch of zeros in here, and really you're interested only on these 2 values. So what we are going to do is click on here to the right, look for the option show non-zero only, and click on there and on this box. And now it significantly simplifies the view of this combined tab. Okay, so again, we have 1.6% of the total composition of the oil. Now we are going to go to the assay option to enter the remaining 98.4% of this oil. Okay, so click on that assay tab, and in here you'll see that there are different options, different tables, and different places here where you will see information. There are 5 steps to enter an assay in the software. Okay, the first step is to give it a name. Okay, so in here you will enter what it says component and the mole percent. Enter the name for this oil, and we will name it assay. Okay, let's enter the name assay here. Let me put it all in capital letters. Assay. That's the component name. And just as a note, you cannot add names that are longer than 5 letters, and also the names should not have any spaces. Okay, so 5 letters, no spaces for the name for this specific oil entry. Then we'll enter here the mole percent. So that mole percent is 98.4. Okay. Then you have a section here that is named entry options. This is the entry options section. And in here, we can select the type of entry. So we are going to select, we have a boiling point curve or a distillation curve. So for type, you'll see if you click in this drop down arrow here, you have different options. You could enter the ASTM D86, some other ASTMs here, but for our example, it was given to us a true boiling point curve or a TVP curve. So let's select that option. Okay. Then we need to define the thermo method. Again, there are options here. Okay. And the thermo method is what the software is going to use to convert the experimental curve, okay, the TVP curve, into pseudo components, and we are going to and with that thermo method we are going to calculate the properties of those pseudo components. Okay. So the software has 4 options: API 8, API 5, Kaved and Kessler. And for this example, we are going to use the API 8. Okay. Then we have basically to define the density and what type of density we are going to use. So there are 3 different ways of defining the density. We have the specific gravity, the API gravity, and also Watson K. Okay, so in this specific example, we are going to select the API gravity. We were given the API gravity, and the value was or is 41. So we enter the value here in this white box. Okay. Then finally in here, we need to define the number of cuts. So what this means is that the software is going to take your distillation experiment and break it down into, let's say, how many cuts? We can put here 12 cuts. And in this case, it's going to break it down into 12 cuts to create 12 different pseudo components. Okay, so that's the information we enter here. And the third step that we need to follow here or need to do is that now we need to enter the data for the distillation curve. Here is where we enter our distillation data, the volume that has been distilled, and at which temperature. Okay, so we're going to enter this information here for the distillation data. Okay, so I have these numbers here in my left window, so I'm going to start typing them so you can also start typing that information. So we have that this value is 1%. So the first value is 1%, and the temperature at which the 1% of this sample was distilled is 26 degrees C. Then we have 5% of distillation, and that was at 41 degrees C. 10%, and then we have that was at 65 degrees C. 20, and that is at, I actually can see this. 1 second, please. 20 would be 88%, 88 degrees C. For 30 is 102. For 40% is 129. And for 50%, we have 167. For 60, we have 208. For 70, it's 241. For 80, it's going to be 279 degrees C. For 90, we are almost done. 90 is 342. For 95 is 358. And for 100%, that is 397 degrees C. Okay. I hope everyone is with me here. I will put from the very beginning again here so that you can see the values. Is everybody with me here? Let's see.
Yes.
I have my chat all hidden so I can't see. Okay. Cool. Perfect. Okay, so once we have entered this information for the distillation curve, the next step is display assay COGS. So we click on this button here to the left under the entry options. And now it populates our assay properties table. Okay, so that means that we have calculated the properties of 12 different assays. Okay, down here you can see all the different properties that were calculated for your assays, for the assay that we entered. So you'll see that down here it says assay underscore followed by the temperature in Kelvin. So that will be this temperature, right? The first temperature that we enter in degrees C. Now you have, the software has converted it into Kelvin. Okay. And for example, in here you can see the software has calculated the molecular weight for that pseudo component, the normal boiling point, the specific gravity, and all the thermodynamic properties, Gibbs free energy, entropy, all of these values. The in here also summarizes the thermo method that was used to calculate this. So with this, we have already breaking this distillation curve into our different pseudo components, and we can go now to the reconcile tab. Okay, so let's go to the reconcile tab. And in this tab, the software summarizes that you had the inorganic values here for nitrogen and CO2, and that was adding up to 1.6 mole%, and that you have your assay, and that adds up to 98.4. The software would have, if you would have exceeded or were below the 100%, the software would have given you a warning here that you're not completed the 100%. Another thing I want to point out is that normally, ideally, not normally, but ideally, it would be nice to have the composition of water present in the oil. But in this case, it was not measured, so we don't have the value and we couldn't put it in here, okay? So, but in this case, this happens to be a high water cut well, and we are going to ignore this mass balance error. Because I will show you with the results that by not having this water amount in the oil analysis, maybe we are going to have like some partitioning of water from the brine to the oil in order to saturate it if it needs to be saturated at these conditions. Okay, so now we can go ahead and calculate this. There are some warning errors here to the right saying that there are certain components that haven't been calibrated for the MSE SRK, but we can ignore it because we don't have any of these components in the oil analysis. Okay, so the software has reconciled this, and then we can go ahead and add our third analysis. And that third analysis is going to be really, really simple. It's going to be the gas analysis. Okay. So let's go back, and we are going to go to the Actions pane and double click on Add Gas Analysis. And in this case, we just change the name to Bathos Gas. Oops. Bathos Gas. And this is going to be very simple. We were not really given a gas analysis per se. So what we are going to say is that we are going to assume that the gas is 100 mole% methane. Okay, so even if we don't enter a value here, the software will assume that you have 100% methane in this gas. Okay, and there is a reason why I am going to use only methane for the gas phase. This is because I want to illustrate the importance of partitioning among the three phases, right? And also because in some cases you will need to make assumptions. You know that you're producing a gas, but you were not given that gas. So if you assume a specific gas, let's say you are producing in this case methane, then the software will calculate. Once everything is reconciled and once you bring everything to reservoir conditions, then you can have an idea of what would be the composition of this gas at the separator. Okay, and I'll show you that once we get to that step. So we will see in this example how the oil is going to partition the gas phase and vice versa, how the gas partitions into the oil phase. Okay, so I think that what we can do now is just go to the reconcile and simply calculate this. It's very simple. Everything is in the vapor phase. And now we can, now that we have all the analysis here, we can go ahead and bring all of these contents and saturate them at reservoir conditions. But at this point, I'm going to stop here just to give you a quick break of 6 minutes. And we can continue creating this example at the top of the hour. So let's go for some coffee and I'll see you in 6 minutes.